Good morning. Here we are once again at the physics video lecture. psci 168 video lecture 9. I have a bunch of stuff we want to talk about today. I'm going to begin with some announcements regarding the notes. So I'll just write here announcement regarding a number of things actually. So first of all, the notes are looking really good in some cases and not fantastic in other cases, but keep taking notes as well as you can. I'm supplying the logic here, so we're building up the theory. If you take good notes, leave space in between, practice everything I do. Some people aren't that experienced with doing mathematics, just practice it. So the notes, we want to do lots of labeled sketches and we also want to print out lots of interesting pictures that illustrate the things that I'm talking about, plus pictures, okay, that you print out. If you don't have a printer, then you got to just draw better, draw really good pictures. That works as well. So keep doing that. Eventually, we're going to have a notebook as the semester develops where you can actually save this for the end, but we want to have numbered pages, okay? Eventually we're going to have numbered pages, so including all your pictures, sketches, everything, numbered pages, 0 to 100, or whatever amount you work out. And then we're going to have a table of contents and an index. So when all is said and done, you're going to have a unique work in which the whole understanding of energy has been laid out. So table of contents, the index, you could get started on any time whenever you find an interesting vocabulary, and the index will be alphabetized, and then it'll list the pages on which that particular word and topic appears. So as this project unfolds, it's going to get better and better. So that's just to remind you where we're headed with this. We've made it quite a ways now into the study of energy, and so I actually want to review couple of things. I brought a pendulum to class because that was a good thing to work with, and I had just kind of told you guys to do it, but let me go ahead and demonstrate some of these things. So first of all, we'll start with the law of the pendulum. This is really important. Time and accurate time measurement are very important in physics. And we started with the number of days in a year, so large-scale time measurement is also important in civilization. The law of the pendulum allows us to get accurate, shorter-scale time measurement. And so the law of the pendulum, I'll just draw the pendulum carefully. So you've got a length of string, and the length of the pendulum refers to the center of whatever little weight you put on at the end. It goes from the center here all the way to here, and then you pull it out to a certain little distance, and there's an angle made, and when the pendulum goes across and returns back to you, that is the time of one oscillation, or the period of one oscillation. And the period of one oscillation is equal to 2 pi square root of length divided by g, where the length is measured in meters. I'll write it out, and this g is 9.8 meters per second squared, and this is in seconds. So here's what I want to do. I brought a pendulum here. I'm going to swing the camera over to our pendulum. Something like this here. think will work. And let's have a look here. There's our pendulum. Fantastic. And I started with 1 meter. Exactly. So we had done a little bit of numerical examples. You'll see my pendulum here. There's a meter stick, goes right down to the center of that golden weight there. And I'm just going to draw it back. Small amplitude is best, so only a few degrees out like I'm showing. Release it and start counting. Okay. Looks good there. So we would count maybe 10 complete oscillations, and you could control it with your own stopwatch. Okay. 10 complete oscillations, and you'll see that really is 2 seconds. The period is 2 seconds. 1001. Okay, so 1001, 1002, 1003, 1004, as we learn to count. Okay. Now I'm going to shorten the thing. I'll just wrap the string up here till I have 25 centimeters out. And of course, everybody can build a pendulum like this somewhere in their house. Let's see, I want to have 25 centimeters. So that's a little too long still. But the 25 centimeter pendulum, that's pretty close. Maybe one more wrap. One more wrap would be too much. So let's do this. Okay, so this is a quarter the length of the original pendulum. And if we count these out, and the thing to do is count out about 10, and you'll see that count out about 10, divide by 10, that's a 1 second pendulum. 1001, 1002, 1003. Okay, so that's what I wanted to show you guys, an adjustable length pendulum. And now we're going to go back to the drawing board. So I'll go back up to here. There we go. I'll stop this guy here. Okay, that'll work. Okay, so now let's calculate. Let's calculate using this formula. Okay, so we have the period of the pendulum formula, which I'll just repeat. T is equal to 2 pi square root of L divided by G. Okay. What you find is that 2 pi over the square root of G is almost exactly equal to 2. Okay? So that's why when you have a meter, you have a 2 second pendulum. So examples. L equals 1 meter, L equals 0.5 meters, L equals 4 meters, and you can just put any numbers you want. We just, actually, the one we did, L equals 0.25 meters, we did those two. The other thing I want us to be able to do with this pendulum is solve for L. So this is one version. 2, we solve for L. This is an interesting thing you could do. Suppose there were a long rope, going up to a tree branch, and you wanted to know how far up that tree branch is. How long is that rope? You can't measure the whole rope. You just attach a weight to the bottom of the rope. Here's a weight, and then you let it swing back and forth. And you use your own clock to time the period of the pendulum. And then that will tell you how long the rope is. So if we solve for L, we can do that. You'll notice we just have to do, we'll do this in 2 steps. We'll square both sides, 4 pi squared L divided by G. So I square both sides of this equation and solve for L. And you guys should practice these things. It's just going to be a matter of cross multiplying and dividing. So I'll end up with L is equal to G T squared over 4 pi squared. Okay? So once again, here was this formula, and we squared both sides. So T squared, 2 times 2 is 4 pi squared. Square the square root, we just get L over G. And now I just cross multiply it. So G times T squared, and then I divide it by 4 pi squared. Good, so you have this formula, and I'll add a question here. Example, how long is the pendulum of period 3 seconds? How long is the pendulum with period t equals 3 seconds? Okay. Well, here's what you do. Leave room in your notes. You guys can do this. You have to take the t, plug in 3 seconds, and square it. So that's going to be g times 9 divided by 4 pi squared. So you can answer any question like that. So you have a short pendulum, a long pendulum. Doesn't matter. You can get the period of the pendulum given the length, and you can get the length of the pendulum given the period. And so we have control over very accurate timepiece. The pendulum's a very accurate clock. The first accurate clocks were pendulum clocks. Okay. So yeah, go ahead and give these a try. Just leave room in your notes. If you have any questions on these, let me know. And if you build your pendulum, go ahead and take a picture of it and print it out and put it in your notes as well. Good, so what else is on our agenda? I'm going to continue the review. Okay, so that was the review of the pendulum. Next, I'm going to review energy, work, and power. In fact, I'm going to start with force. And this is the type of review we'll do very often because we're just trying to become familiar with these concepts. So we have time, and we notice we need a good length measurement to have this pendulum time measurement, so we have a meter stick. Okay. Meter divided by, powers of 10, which is very nice. That along with scientific notation, we can do anything. Okay, so next, we're going to review force, which we know is a push-or-pull. It has the unit of newtons, and we never forget the weight is a force. I brought my bowling ball here. We'll talk about that in a moment. Weight is a force. And I'm going to add something I haven't had here before. 1 liter of water weighs approximately 10 newtons. Weighs approximately 10 newtons. We'll see later it's 9.8. I'm a little stubborn on force and mass, so we haven't introduced mass yet. Okay, we use the word, but we haven't introduced it formally. So it's all about forces. We have weight. It's a force, and if you want to have that force around to compare things, you've got a liter of water, approximately 10 newtons. 9.8 newtons exactly. Okay. Good, so there's our first point of review. Then we have work. Okay. So work is force times displacement. And the unit of work, it's the Newton times the meter is the joule, so we should be familiar with those. And I want to give 3 examples now, 2 of which we've already done. So one was the grandfather clock. And I forget what exact numbers we used, right? They can vary depending on how we define it, how big of a weight we use. The second one was the stair climb. Okay, and for the stair climb, I think I remember my numbers. Yeah, we did. Work to climb the stairs was 800 newtons times 5 meters, right? So if you look in your notes, we had 4,000 joules. And we started at the bottom and ended up at the top here. So that's what we're doing. Stair climb takes work 4,000 joules to get to the top, according to my other example. Now, the question is, can we store work? Can work be stored? Question mark. And the answer is yes. When I wind up the grandfather clock, as long as the weight just stays there, it's stored, and then if I set the clock in motion, it will eventually, the weight will drive the grandfather clock for a week. Okay? So the work can be stored. Now, how about the stair climb? Can I store the work that I did on the stair climb? And I'll give a third example. And maybe I need a little more room for a picture on this one. So the grandfather clock was a handful of joules. Me climbing the stairs, 4,000 joules. My third example, and now I've asked, can work be stored? My third example is water in a lake. It's precisely water in a lake up in the mountains somewhere. So my third example, bring this down to this board here. One cubic meter of water weighs, notice I had a liter there being about 10 newtons, so a cubic meter of water weighs 10,000 newtons. Approximately 10,000 newtons. So suppose you have water in a lake, and this is already getting into our hydropower way earlier than I usually do, but we got a long ways to go to get there. But so yeah, we've got this cubic meter of water out of many cubic meters of water in the lake, and the power plant is going to be down here on the side of the mountain. In fact, it's going to be 1,000 meters down the side of the mountain. Well, if we just call it, if I had to go from down here and climb up to that lake and carry water up there, how much work would that be? 10,000 newtons times 1,000 meters, force times displacement. So 10 to the 4th newtons times 10 to the 3rd meters, now we don't want to write too many zeros out here, would be 10 to the 7 joules. That's a lot of work. 10 to the 7 joules. Can the work be stored? Well, it's stored up there. Well, there's a name for stored work. Okay, so we have these 3 examples. Stored work we can call potential energy. And now you guys remember what I call energy, the capacity to do work. So that makes complete sense. I can store the work, means I'm storing energy, means I'm storing the capacity to do work. So this water up here represents potential energy if I can somehow get it to do work. The grandfather clock weight was the most direct example because we saw how it can do work. Now these 2 examples I'm going to explain with a bowling ball. Just bear with me here. Okay. So I think we agreed that the bowling ball weighs 70 pounds. Let me check my camera angles here. Yeah, let's go like this. 70 pounds? No, 70 newtons. Okay. So there's my meter. Okay. I'm just going to guess how high the meter is. Yeah, that's right. Okay. So if I lift this bowling ball, I just did 70 joules of work. If I could hang it up somewhere, I could store the work. Or you could say, well, just hold it there and you're storing the work. Okay. Well, that only goes so far. Now here's the thing. Let's make this an experimental type of discussion. So here's our idea. We lift the bowling ball. Okay. Here's our 0 level. Here's 1 meter. And you guys, you all saw me lift the bowling ball 1 meter. Okay. So this is 70 joules. And I need a little more room here. 70 joules equals 70 newtons times 1 meter. Now suppose I were to drop this, and I don't have the model. Well, I do have a model. Suppose this were a spike. The pen's the spike, and I drop the bowling ball on the spike and drive it into some wood or drive it into the ground, okay? And the spike is this long, and that happens to just be 10 centimeters, okay? So we drop it onto that spike here. Here it is. Got a sharp point. We drop the ball onto the spike and we drive the spike into the ground or into the wood or whatever we're driving it into. And that is force times displacement as well. So that is also work. So right here, the ball is moving and it's about to drive the spike. Then we would say the work is equal to some question mark of newtons times 0.1 meters, because the displacement of the spike is only 0.1 meters. And if these are equal, then what's my mystery number there? Instead of 70, it would be 700. So 70 joules is equal to 700 times 0.1. Okay? Or the work is equal to 700 newtons times 0.1 meter. Okay? So not only did I store the work in a number of ways, with the water, with the grandfather clock and so forth, but I was able to get the work back. So the stored work, which is called potential energy, I have that right here, can be used, so potential energy can be used to do work. So this is very, you could say, logical definition And this is a way for me to segue into a topic we have, because there was motion here in between. So I did the work, okay, stored it, and I let go, and a second later it did some work down here. But what about the in-between? So we're going to have to relate energy, right? Stored work, potential energy. We're going to have to relate energy and motion, which means we have a whole section on motion to do before we get there. But that was my way of well, there's a transformation of different forms of energy here. But that's my segue into the science of motion. Let me consult the clock here and see how we're going to do this. Okay, very good. So I'll add to this discussion point here. So, work, and here I'll call this, I'll refer to this thing over here. Work can be converted to motion, and motion is just the bowling ball falling. I'm not going to drop it for you, but you get the idea. And the motion can be converted to work again. To work again, and the whole time we're talking about energy. Okay, good. So I'm going to go back to the drawing board. I'll bring the camera up to both boards again. Okay. And yeah, this whole point here, tying all these concepts together, we now have to study motion, and that is its own lecture or two. So here's how our list is now looking. So we have force, work, now I'll write potential energy, okay. Now when we had the pendulum, we had time, so we have power was work per time. See, so we had to study time, we had to study force, lengths, get the potential energy concept. Power, work over time, we had to study time, which we've done. So, time, then the pendulum. Pendulum was also an example of motion, and tying all these things together, we now have to study motion. So next, study of motion. So that's how we're leading up to the study of motion. I'm going to leave this lecture off right now. You got a good chance to practice some of these things. Build your pendulum, take some pictures of it. Next time, I'll go straight into the study of motion, and we definitely need a full hour on that, because we're not hiding anything here. You know, we're getting the full value, the full treatment. So we'll study the motion, the various laws of motion, and then we'll be able to come back to these concepts with a deeper understanding. So that's our plan, and we'll see you guys next time.